Okay, so welcome to lecture number 28 of this stack thermal course. So in this particular lecture, so previously we told you that what will be the effective degeneracy for diatomic for diatomic molecules. So and we have also said what is spin splitting, okay, and gamma doubling and stuff like that. Usually we say that the energy difference that is produced by gamma doubling is usually much smaller than that produced by spin splitting. So in accordance to it, okay, we now can generate these kind of tables, which is basically the electronic energy levels and degeneracies for oxygen here. Okay, now here, if you look at it carefully, if you look at this particular diagram, you will see that each electronic state is defined by a unique Morse potential. We already covered what is a Morse potential. So for each of this electronic energy state is represented by this unique Morse potential. Okay. So, and also the rule is that for molecules with a ground electronic state is designated by X. The ground electronic state is represented by X. Okay, and each higher electronic state with the same multiplicity is labeled as A, B, C, etc. A, B, C, etc. Similarly, excited electronic states with different multiplicity are given by this nomenclature small a, small b, etc. Okay. So you understand that ground state electronic states are, and each higher electronic state with the same multiplicity is labeled as capital A, capital B, capital C. Whereas the excited electronic states are represented with different multiplicity are related as A, B, C. So that is what you get. Now, if you look at this particular table now, okay, if you look at this particular table now, you will find that if you look at this particular table, okay, this is for oxygen. So you can see, for example, let's take any one of the figure. So this TE that you see over here, TE, okay, TE is nothing but represents the gap between minima in Morse potential, okay, describing okay, the ground electronic state, and okay, each excited electronic state. Okay. So it also, so if you look at this particular table now, you will find that the effective degeneracies is also given here. The effective, and this is TE. Okay. So, and this is the nomenclature that we have already established, right? That delta, sigma, okay, and ABC, we already noted what those things are going to be. But there are a couple of plus minus signs that we see, which will come to it in a little bit. Okay, so now similarly for excited electronic states of different multiplicity, we know what it is given by. Okay, now you can see certain subscripts G and U. Okay. The G/U subscripts are denote the symmetry of the wave function, even/odd upon reflection, to the midpoint of the nuclei, midpoint of its identical nuclei. Okay. Finally, the superscript like minus and plus, they designate what we call the symmetry of the wave function. When reflected okay, through an arbitrary plane, okay, passing through both nuclei, of a diatomic molecule. Okay, so you can now have a very good idea of what it is. So now, what to recap, each electronic state is represented by a separate Morse potential, which we see over here. Now, if the electronic state has got the same multiplicity, it is designated as capital A, capital B, capital C. These are every higher electronic states compared to the ground state. Ground state is always represented as X. Okay. Similarly, each excited electronic states with different multiplicity is given the symbol small a, small b, small c. And the total and TE is basically the gap between the minimum in Morse potential describing the ground electronic state and each excited electronic state. Okay, so that is given as TE. So as we see that when it is the ground electronic state, which is given as X, T is obviously equal to 0, and the effective degeneracy is 3. So we know why it is going to be 3. Okay. Now, this is an excited state for which there is a TE. Okay, and the effective degeneracy is given as 2. Similarly, this is an even higher excited state because A, B, C are in order of increasing energy. That means B has got more energy than A and C has got more energy than B. So naturally, you see that B has got a higher energy compared to A, and that is given as the degeneracy. Moment now you go to the another, a different electronic state altogether, higher electronic state with same multiplicity now. Okay, so that is given as this is T, and so B is higher than A, so it is given as 49793. These are the corresponding degeneracies that you have. So X is always given as TE equal to 0, okay, because this is the minima of the Morse potential, okay, to the minima of the corresponding gap between the two minimas, essentially. So this is what is your TE. Okay, so this is written as T. All right. So that is what the intermolecular symbols looks like. Now we can write down now the combined energy, energy modes for atoms and diatomic molecules. Okay. So typically, Schrodinger's wave equation gave us what? Electronic, vibrational, and rotational. So what did it give us? SS wave equation gave us a few things. One is electronic, which we just described in details. One is rotational. One is vibrational. These are the different modes. that we got. Okay, and these are the different energy levels that we saw. For atoms, our task was easy, as electronic motion underlies the only internal energy mode. So for atoms, okay, we could only say that electronic motion okay, electronic motion was the only internal mode. All right, internal energy mode. So typically, energy level diagrams are constructed by setting the energy of the ground electronic state to 0. Okay, so if we consider that the electronic energies for the hydrogen atom, it was like this: minus RH by m squared. Sorry, n squared, where RH was the Rydberg constant, and the zero of the energy is when n is equal to 1. This is the zero of energy. All right. And therefore the electronic energy was written as 1 over constant 1 minus n squared. Okay, so this was for atomic hydrogen. We all got this. Okay, now in contrast to monoatomic species, the internal energy of a diatomic molecule. So if we move on to internal energy of a diatomic molecule, okay, can be obtained by summing. So what we can do is that we sum contributions from electronic, okay, vibrational, okay, and rotational energy modes. So this time our assumptions were rigid rotor, okay, and we also had the harmonic oscillator. Okay, so for the rigid rotor it was BE. This is the rotational and the vibrational, and this was omega E. Okay, so rotational and vibrational. Rotational. This is vibrational parameters. Okay, so in addition to this, if you now recall the equations that we already did, and let me just write it down here for the sake of convenience. So if you recall that if we recall, okay, that Fj was given as, okay, j into j plus 1 into be, okay, where j is equal to 0, 1, 2, da da da, and be, if you recall, was written as h by 8 pi square c I e. Okay, so that was what we wrote, and then of course other equation that we are going to use over here is given as V. We write it as V. Vibration divided by H, given as E plus half into WE, equal to 0, 1, 2, da da da. Okay, so therefore, once we know these two expressions of Fj and Ev, therefore we can write the internal energy as TE plus V plus half WE plus J into J plus 1 into BE. So all these are in centimeter inverse. Okay, so if we look at that associated energy in energy level diagram, this is how it should look like. Okay, so you have, let me try to draw it the best I could. Okay. So the difference between this and this is given as D. So this is your X, this is your A. So this is equal to 0. Okay, now let us use a different marker. Okay, so what you see that these are basically the vibrational levels. TE is the difference between the two minimums that you are talking about. This is A, one level higher, and this is V equal to 0. This is not at the end because of the 0 point energy. So this is 0 point energy. Okay, now you go to the other level here. Another thing here, and this, like that. So now you have all right. So this is once again V equal to 0. Okay, so these are again the vibrational levels. And these that you see, these are the rotational levels. These are the rotation. All right, so you know that what are the different levels. So the vibrational level actually, you know, occurs above the bottom of each well. Okay, so what we see over here, that TE, okay, identifies there is a very sizable energy gap, sizable energy gap between the bottoms of potential wells. Okay, so the electronic energy is portrayed by the Morse potential. The ground vibrational level V equal to 0 is actually a little elevated, occurs above the bottom, occurs above due to 0 point energy. Okay, so so each electronic state, we already said, is represented by a Morse potential. Okay, so so the spectral lines can all be ascertained by using these energy gaps that are shown in this particular diagram. So this is the diagram, sample energy level diagram that we have. Okay, and each electronic state, as we said, is represented by, each electronic state is portrayed by the corresponding Morse potential that we already said earlier. Okay, so such we can see that there are all possible energy gaps, right? From here to here, here to here, within the rotational band, from one rotational band to one vibrational, all these. So there are many, you can see that the spectral lines, if we look at it, spectral lines, okay, can occur, or would arise, okay, corresponding to all energy gaps. But fortunately, that is not the rule. There are certain selection rules which makes life a bit easier. There are selection rules now which makes the life a little bit easier, so to say. Okay, so just to have a clear insight now. So now that we know all these things, we know what is spin splitting, what is doubling, and all those things. We now know what are the different electronic energy levels, the corresponding degeneracies, everything we know, especially for diatomic. And now we also have the combined energy, how we can write those combined energies. So all these things are there with us. Now, armed with this, okay, we should now start looking at the selection rules, right? The selection rules for atoms and molecules. The selection rules for atoms and molecules. That is something that we need to know. So selection rules, what are selection rules? Selection rules are basically restrictions that govern the possible or allowed transitions between rotational, vibrational, and electronic states. Okay, so for each energy mode, such rules are typically in terms of the permitted changes in the characteristics quantum numbers. So what these rules are in terms of permitted changes in the characteristic quantum numbers defining internal energy states. So these rules are in terms of the permitted changes in the characteristic quantum numbers defining internal energy states. Okay, so in general, we observe the spectral intensity of an allowed transition is much greater than that for a disallowed or forbidden transition. So we're going to use terms like what is forbidden transition, what is allowed transition. Okay, so for electronic mode, the term symbols distinguishing atoms and molecules generally provide the basic nomenclature that is required for the construction of the selection rules. In this case, allowed transitions normally involve jump of a single electron from one orbital to the other. While selection rules, these are experimental, there has been also significant theoretical confirmation by what we call the application of the perturbation theory. So perturbation theory is something that you apply to the Schrodinger's wave equation. And then we can see that once there is a perturbation, if we apply it for a generic two-level system, and therefore we define based on that what are the transition probabilities associated with such transitions. But the idea of selection rules is that what characteristics quantum number changes are permitted, and this can be done, and what is called forbidden transition and what is called allowed transition. And spectroscopically you can do a lot of these things, but non-spectroscopically, if you want to do it a theoretical analysis of this thing, therefore you apply what we call a perturbation theory on the time-dependent Schrodinger's wave equation. So just recall, so this was the time-dependent Schrodinger's wave equation. So this was the time-dependent. So you apply a perturbation on this, apply a perturbation on the time-dependent Schrodinger's wave equation and determine the transition probabilities. So what is going to be used for? To determine the transition probabilities. So that is what we are going to do over in the next lecture, that we are going to define the transition probabilities associated with. So these are transition probabilities associated with rotational, vibrational, and electronic modes. Okay, and this all comes from the Schrodinger's wave equation, that time-dependent Schrodinger's wave equation that we have. Okay, and this is done for a generic. We are going to do it for a generic two-level system. Okay, a generic two-level system, and we are going to, using that, we are going to use and find out what will be the corresponding transitional probabilities. So in the next class, we are going to go through this particular motion and see that how we can perturb the Schrodinger's wave equation and what solutions we are going to get out of it. So still next class. Thank you.